Okay, so this is our lesson on solving rational equations, and we're going to solve some simple rational equations, and we're going to talk about some things you have to be careful of when you get your final answer, and finally at the end we'll look at a few word problems as well. So let's get started. So let's look at this first example, 2 over x plus 2 equals 2x plus 1 over x plus 1. Now, the way that I'm going to solve this might not be the same thing that you do, and that's okay. I'll show you another method at the end that's probably going to look more close to what you would do if you were to do this question on your own. Because what I'm going to do to start actually is I'm going to bring this over to the other side and set the equation equal to 0. So that was my first step. My next step is to simplify this rational expression by finding the lowest common denominator so I can make this into a single rational expression. Now that lowest common denominator is going to be x plus 2 times x plus 1. So that means I need to multiply 2 by x plus 1 and 2x plus 1 times x plus 2. And I can put those together once I do that. Now the next step, you have a couple choices here. You could simplify the numerator, but what I'm going to do instead first is I'm going to realize that this is helpful because what I can do now is I can multiply both sides by the denominator. So multiply both sides of the equation by x plus 2 times x plus 1. And when I do that, well, I still get 0, of course, on the right side, but on the left side, I'll multiply by x plus 2 times x plus 1, and the x plus 2, x plus 1 here will divide out. And so I no longer have a rational expression. And now it's just a matter of solving. This is actually, if you look at it, it's a quadratic equation. Multiply by 2 here, and then use FOIL here. So 2x times x, 2x times 2, 1 times x, 1 times 2. Okay, now be very careful here. You're subtracting the result of this multiplication, so you need to leave the brackets there to make sure that you do that correctly. The 2x, you'll have a minus 2x squared. You're going to have a 2x minus a 5x, which is negative 3x, and then 2 subtract 2 is 0. So I get 2x squared minus 3x equals 0. I can factor that, and I get negative x times 2x minus 3, which gives me solutions of 0 or 3 halves. Now, one thing I'm going to mention in this solution, and this is the final solution, is that if we look at this equation up here, we see that there is an x plus 2 and an x plus 1 in the denominator. That means that x cannot equal negative 2 and it cannot equal negative 1. And that statement that I've added should probably be there, and it's true the whole way down. So for example, when I get to this step here, and I've reduced this problem to solving this quadratic equation, I should notice that it's only has the same solutions as this equation if we remember that this has to be true as well. X can't be 2 or negative 1. Now, as it turns out, we're fine. Those didn't end up being any of our solutions. So it's not really important in this example, but I think we'll find out that that gets to be important in some other examples. The other thing I'd like to bring up as well is that every time we solve an equation, there should be some type of graphical representation of the solution. You're quite capable of graphing the left side and the right side of this equation and then sketching them and then seeing where they intersect, and they should intersect at 0 or 3 halves. Now from your graph, you might not be able to tell exactly where they intersect, but you could certainly see that that's reasonable. I'm going to throw these in Desmos for now, and you'll see what I mean. Okay, so I've plotted the left side of the equation and the right side of the equation separately, the left side of the equation in red and the right side in blue, and you can see them in Desmos. And sure enough, we find out that they intersect in 2 spots, one that x equals 0, okay, which is one of our solutions. Notice the y value here doesn't really mean anything. We're not looking for a point of intersection, we're just looking for when these expressions are equal. They're equal because they're both equal to 1 when x is 0. And then our other one, sure enough, at negative 1.5 or negative 3 halves. And then the 4 here, it doesn't mean much other than, when x is equal to negative 3 halves, these two, both sides of the equation are equal because they're both equal to 4. And so there's your 2 points of intersection. Or sorry, there's your 2 solutions shown graphically. Now if I go back and look at this example again, a lot of people would want to cross multiply here, and that is absolutely fine. You can definitely cross multiply. You get the exact same solution. You get the exact same quadratic equation that you get down here. Really what you're doing when you cross multiply is it's a shortcut for finding the common denominator and then multiplying by the common denominator. So when you multiply 2 by x plus 1, like you did down here, and 2x plus 1 by x plus 2, which you did down here, like I said, it's kind of like a shortcut for finding the common denominator and then dropping it, which is multiplying by it. So feel free to do that. You are definitely allowed to cross multiply when you have two rational expressions that are equal to each other. It's the only time that works. So the next example is quite a bit more complicated. You can't just cross multiply here. So, but what you can do to make it look like the previous example is you could combine all the rational expressions into one. Now the first step I actually do here is I'm going to factor this denominator. Okay, so I did factors to x minus 1, x plus 1. Then I'm going to find a common denominator for all three terms. So I notice that the lowest common denominator is x minus 1 times x plus 1. Since this denominator is x plus 1, I can just multiply it by x minus 1. And since this denominator is x minus 1, I can just multiply it by x plus 1. So I don't multiply all the denominators together. It's kind of like when you have, you know, a sixth plus a third. The lowest common denominator here is not 18, it's 6. You can multiply this one by 2 to make it 6. Here I can multiply this one by x minus 1 to make it the same as this denominator. And I can multiply this by x plus 1 to make it the same as this denominator as well. It's exactly what I've done. Multiply by x plus 1 here, x plus 1 here, x minus 1, and x minus 1. And then I multiply by the lowest common denominator. A lot of people like to say they're dropping the denominator. I don't really like that language because you're not just dropping it, you're multiplying by it, or you're realizing that if the denominators are all the same, then the numerators have to match up. That's another way of looking at it. Okay, but in either case, we got another quadratic equation here. So we're going to solve this by expanding it and setting it to 0. Okay, x minus 1 times x minus 1, x squared minus 2x plus 1, and then I use FOIL here as well to get x squared plus 8x plus 7. And then I'm going to expand the negative, so I get negative x squared, think about multiplying by negative 1 here, plus 2x minus 1. Okay, be careful with that, that's where a lot of students go wrong. They'll write negative x squared minus 2x plus 1 and forget that the negative sign distributes over the addition and subtraction there. And then if I bring everything to the right side, I get 2x squared plus 6x plus 4 is equal to 0. I notice everything here is divisible by 2. So it's the same as x squared plus 3x plus 2 equals 0, which does factor to x plus 2 times x plus 1 equals 0. And so our solutions are x equals negative 2 and x equals negative 1. Now, this is a bit of a trick question. There's something else going on here. Can you see what it is? Well, let's go back at the top. This equation clearly has some restrictions. You cannot have x equaling 1 or negative 1. So plus or minus 1. Just get rid of this. So that is true all the way down. Okay, that's even true here. On this line right here, it's not obvious that x can't be 1 or negative 1. You can actually sub a 1 or a negative 1 into this equation here. So as it turns out, this original equation and the equation I've starred aren't equivalent unless you keep in mind that x can't be 1 or negative 1. Why are they not equivalent? Well, they're not equivalent because here, if I sub in a 1, I get an undefined value. Okay, it's right here and right here. And so the equation wouldn't be balanced. It doesn't even evaluate to anything. So that also has to be true right here. If this is supposed to represent the same solutions as this, then we need to keep this idea in mind. And sure enough, we got x equals negative 1 as an equation. That can't be true. So we take it off, okay? X can only equal negative 2. If you sub x equals negative 2, into the equation up here, you will find the equation is balanced. Right side equals left side. If you sub x equals -1 into the equation up here, it's not balanced. You can't balance it because it's undefined. So it doesn't evaluate to anything. Okay, you have 4 divided by 0, and you have x plus 7 divided by 0. So, or sorry, not x plus 7, but x minus 1 divided by 0. So that is the trick. Now this answer that we end up throwing out is called extraneous root. And what that extraneous means is it's a solution that appears to be correct, but when we check in the original equation, is not correct. And how does it happen? Well, it's actually, I mean, I've sort of pointed out with the star here, it's actually this line to this line that creates the extraneous root. And it does that because you're multiplying everything by these values right here, the denominator, and that's what introduces an extraneous root. Anytime you do that in math, when you multiply by a variable you're trying to solve for, you're in danger of introducing an extraneous root. I can show you a really silly example of where you might do it. So imagine you had something like x minus 1 equals 0, and you're trying to solve that equation. Well, clearly 1 is the solution to that equation. 1 minus 1 is 0. But suppose I were to multiply both sides of the equation by x plus 1. I can do that. I can multiply by whatever I want. And then I expand it. And I get x squared minus 1 equals 0. And then I would say x squared equals 1. Therefore, x is positive or negative 1. Well, okay. Yeah, x squared minus 1 equals 0 does have the solutions of x equals plus or minus 1, but x minus 1 equals 0 doesn't. So do you see how I'm able to sneak in this minus 1 as an answer that doesn't actually exist? In fact, if I have x minus 1 equals 0, I can multiply by whatever I want and introduce any extraneous root that I want to. Okay, if I'd multiplied by x plus 5, then I could say negative 5 is also a solution to that equation. So you have to be very, very careful with that. The other time it happens sometimes is if you square both sides of an equation, you'll often introduce an extraneous root by doing that as well. With rational equations, sometimes there's an extraneous root and sometimes there isn't. As you saw in the first example, there wasn't and there was here. So moral of the story is when you're solving a rational equation, you should always make sure that you don't have any of these answers that shouldn't count. Now we'll move on to a couple word problems, and these can be tough if you haven't seen them before. They're definitely challenging. In this example, we have Alvin, who's attempted 20 free throws. So in basketball, of course, when you take a foul shot, we sometimes call that a free throw. And he's made 40% of them. And suppose he wants to, he'd like to make 60% of his free throws. How many consecutive free throws, must he make to increase his percentage to 60? So imagine he's done his 20 free throws, he's made 40% of them. Now, how many do we need to hit in a row to bring his final percentage up to 60? Now, you could probably guess and check this answer, but let's do something a little bit better. Okay, the first thing I would do here is I would say introduce a variable. Let x be the number of consecutive three throws. Okay, not three throws. Free throws. Hard to say. Free throws. Say that 5 times fast. Let's x in the number of consecutive free throws Alvin must make. And then, of course, x will be our answer then to this question. I mean, the first thing I would also do here is I would look at this and say, well, what's 40% of 20? How many free throws did he make? That turns out to be 0.4 times 20, which I believe is 8. So he's made 8 free throws. Okay, so let's think about calculating his free throw percentage. We want it to be 60%, which means when we divide a fraction, we should get 0.6, which is 60%. Well, how many free throws has he made, and how many has he taken? Assuming that he's successful in this little goal of increasing it to 60%. Well, he's made 8 already. He's hopefully going to need to make x more, so 8 plus x. The total shots he's taken are 20 so far, but he'll have to take x more. And so this equation right here is actually going to give us the solution. He makes 8 free throws plus the consecutive ones at the end, divided by 20 total plus the consecutive ones at the end, and we want that to equal 60%. Now, this step's not necessary, but I think it makes the problem a lot more interesting, is if, or a lot like a neater answer, is to take 60% and change it to a fraction. So 60% is 60 over 100, which reduces to 6 over 10, which reduces to 3/5. So we can change 60% to 3/5. And now this isn't that difficult of an equation to solve for. Keep in mind when we do this, x can't be negative 20, but we can actually go further and say, look, because you can't take negative free throws, that's impossible. So x has to be greater than 0. And if you want, you can bring this over, bring the 3/5 over, find the common denominator, or like I said before, you're welcome to cross multiply, which I'll do in this example. So 5 times 8 plus x equals 3 times 20 plus x. And in this case, we actually just have a linear equation. It's not even quadratic. So let's finish it off here. 40 plus 5x equals 60 plus 3x. That means that 2x, okay, 5x minus 3x would equal 20, and x equals 10. So he must make 10 free throws in a row in order to bring his percentage up to 60. And of course, that would be 18 in total he made out of 30. So there you go. Okay, last question in this lesson. So if Melanie and Dawn work together, they can clean their house in 6 hours. This would be a pretty big house. That's a long time. In any case, if Melanie does it herself, she can do it in 10 hours. How long does it take Dawn to clean the house himself? Well, we're going to make an assumption here that when they work together, they're just as efficient as when they work alone. In real life, that might not be true. If Dawn was as fast as Melanie, that would mean we'd expect Melanie to take 12 hours to clean the house on her own. So clearly Dawn isn't as quick of a cleaner as Melanie is. This is a tough question. If you've never seen this before, it's a difficult one to get started. Once you do get started, it's not that bad. So the way to start is to look and see, like, let's start by defining our variable that we're looking for, t. So let t be the amount of time it takes Don to clean the house himself. Now let's think about Melanie, who cleans the house in 10 hours. Well, basically, the little trick to this one is to realize that that means that Melanie works at a rate of 1/10 of the house per hour. So she cleans 1/10 of the house every hour. Whereas Dawn works at a rate of 1/t of the house per hour. So we don't know how long Dawn takes, but if t is the amount of time he takes, like say it would take him 15 hours, then he works at a rate of 1/15 of the house every hour. Together, they work at a rate of 1/6 of the house per hour. So every hour, the two of them clean 1/6 of the house every hour. We can take this information, turn it into an equation we can solve, and that's going to give us the answer. So think about this question and see if you can get the equation. If I take Melanie's rate and I add it to Dawn's rate, then I should get the rate when they're working together. And that's your equation right there. That'll give us the final answer for t. How do we solve this? Well, the first thing to do would be to find a common denominator. In this case, notice that 10 and 6 both go into 30, and we need a t in the denominator as well. So our lowest common denominator in this case is 30t. Okay, you would get 60t if you multiply them all together, but 30t is a little lower, so a little easier to deal with. Okay, so now I need to think about how do I make each of these equations into equations with denominators of 30t, so that I'm going to get something like this. Okay. The numerators are all equal to 1. So what I do for each of these, I just look at them one by one. I say, what do I have to multiply 10 by to make it a 30t? The answer is 3t. So I multiply 1 by 3t as well. Okay, what do I have to do to t to make it 30t? I have to multiply by 30, so I multiply the 1 by 30 as well. Okay, just look at that and make sure that makes sense. 30 over 30t reduces to 1 over t, and 3t over 30t does reduce to 1/10. So make sure that what you're writing down makes sense. Finally, for the last one, 6 times 5t would equal 30t, so I multiply 1 by 5t as well. Okay. Notice that t can't be 0 here. Okay. T has to be greater than 0 in this example, so just nice to think about that when we're working on this. Multiply everything by 30t, and we get 3t plus 30 equals 5t. Okay, that means that 30 equals 2t, or t is 15. It takes Don 15 hours to clean the house on his own. Okay, that's the end of this lesson. Thank you.